Let's start. But before we introduce the main content today, let me introduce you a concept which is related to your assignment one, unfolded CFG. So unfolded CFG is actually just a CFG with loops unfolded. So the reason of because this is a normal CFG and this is an unfolded one, and if we try to unfold CFG, a CFG, we try to flatten the loop into basically we just copy the body of the loop multiple times to represent different numbers of iterations. So this is called unfolded CFG. And you may think that, okay, this looks tedious and we have to limit the number of iterations to do this kind of unfolding. Otherwise, this graph can grow very, very large. So why do we still need this? And this kind of unfolded CFG is actually to clearly show the path, the execution path across different iterations of the loop. So if we don't unfold the CFG and we loop multiple times, we have to draw the path in this CFG multiple times. But if we unfold it, is like just a linear path. So that's why we do this kind of unfolding here. So in your assignment question, you need to draw this kind of unfolded CFG. So that's about this concept, and let's start the main content today. So, but before we start, let me ask you a question. Do you think how difficult do you think is assignment one? Is it difficult or is it easy? Easy. Or difficult? Oh, some of the questions could be ambiguous, right? Even after the clarification yesterday? Can you post them on the forum so I can answer? And what about the difficulty of the questions? So, like moderate or hard or easy? No response. I'll take it as easy and make assignment 2 harder. And okay, let's start today's content anyway. So in today's lecture, we are going to learn different levels of testing. And here is the outline today. So we are going to have a look at the overview of different levels of testing. And then we look at 2 levels today. So we will first go through unit testing, and then we will go through integration testing. So what we have learned so far are functional testing and structural testing. These are actually some black box and white box testing methodologies which could be used to test requirements of the program or implementations of the program. So this helps us to design the test cases to comprehensively explore the different states of the program from different angle, from the requirement angle or from the implementation angle. However, this may sound differently. You may have heard about, okay, some kind of test-driven development or maybe unit testing. So these functional testing and structural testing may sound different from what you have heard about before. So what we are going to learn next are the different stages or different levels of testing which are related to the development activities. So we will take a look at the same problem from a different angle, from the stage point of view. So, and all of them are actually methodologies for designing tests. So these are all the basic methodologies which you could apply to different tools, different testing tools, or different programming languages, or different targets. But you have to choose which methodology you use. But they are all very generic. And we are interested in this lecture, in this course, we are interested in 3 different levels of testing. The first level is called unit test. The second one is integration testing, and the third one is system testing. And this is an illustration of different levels of testing. You can see that for unit testing, we try to cover each individual component of the program. And for integration testing, we try to connect some components together. But you may see that there are some overlappings. There could be some overlappings between unit testing and integration testing, because sometimes we cannot connect every individual component to unit. So as you can see, for system testing, we just try to connect everything together and test the entire software as a whole system. And the key about different levels of testings are how should we determine the nodes in this graph and the edges of this graph. So this is a key of how we determine different levels of testing. And as I just mentioned, determining levels of testing is related to the development activity. And you may have learned about software development lifecycle before, right? SDLC. And in this V model, you may encounter this model a lot from the internet or from other sources of information. So, but different information sources could have slightly different, could use slightly different terminologies. But this is the one which aligns with our content the best. So for SDLC here, we use the waterfall development model here. So what we do is, first we do planning. We plan how we develop the software. And then we do requirement analysis, requirement engineering. And after that, we design the architecture of the software. And then we do detailed design, and then we implement the software. And on the right-hand side of the V model is the software testing life cycle. So as you can see, in each of the development stage, we do have a corresponding testing stage. And this is how we determine different levels of testing. As you can see, in the bottom, we have unit testing, which is related to testing the detailed design. And if we go one layer up, we have integration testing, which is to test the interactions between each of the individual component. And after that, we have system and acceptance testing. So, which is to test the entire software against the requirements. And for system and acceptance testing, you may think that, okay, we are going to learn unit test, we are going to learn integration test, we are going to learn system test, but what is acceptance testing here? So actually, you may have heard about alpha testing and beta testing. So these are actually 2 types of user acceptance testing. So acceptance testing is to test whether a piece of software is acceptable to a certain party. So for example, for users, we can do an alpha testing, which is to invite some internal users or some invited users to try to use the system to do the testing. And for beta testing, which is to release the software to the public and tell them that this is a testing version. This is a beta version, so maybe the user data is not could be collected, and maybe your whatever activity you have done with the software may get tracked. So this is beta testing. And also we do have some kind of other acceptance testings like business acceptance, or more importantly, regulation acceptance for some safety or security critical software. So this is acceptance testing, but we won't go through the details of acceptance testings in this course. And now, that's all about different levels of testing. So basically, the idea is to have one particular testing plan for each of the development stage, and we try to develop tests according to the different levels. And the first level we are going to learn today is called unit testing. And you may have heard about this before, and maybe you have used some of the frameworks before. So unit testing, this is a formal definition, which is always a bit boring, but I will highlight some keywords here. So unit testing is the process of taking a module or an atomic unit and running it in isolation from the rest of the software product by using prepared test cases and comparing the actual results with the predicted results according to the specification of the design module. So this is a quite long definition, and we do have some keywords here to highlight. So the first one is, for unit test, we need to identify the atomic unit for the program, and then we need to run this atomic unit. This running here means that this process is dynamic. We need to execute the code. This is dynamic. And then we need to have some prepared test cases or prepared test inputs to run this unit. And how can we prepare this test input? We can use the strategies we have learned from functional testing and structural testing. And another important thing here to notice is that we need to compare the execution result with some expected results to report errors or bugs. So if you have done some unit testing before, you may notice that you always need to write some kind of assertions at the end of the test case. So this one is also very important for unit test. And in short, unit testing is the process of testing the smallest isolated unit that could be tested. So this is a less formal definition here. And why do we need to do unit testing? Why it is important? Because if we test the modules individually, it is normally easier for us to generate test cases. For example, if you try to do some boundary value testing or some structural testing with a simple component, a very small module, then it is much easier than doing this kind of testing design for large or complex modules, right? So that's why unit test is often simpler than doing some more complex testing, and it is often more exhaustive because we are trying to divide the large program into smaller modules, and we can somehow exhaustively test all the small units. So it is considered exhaustive. And unit testing is actually part of the test-driven development. So when you do test-driven development, the test cases you are writing are actually unit tests. So you can't really write test cases for a very big requirement or for the entire system and then do the development. And that doesn't make sense So what makes sense is you write some test cases for a smaller piece of code, and then you try to write the code to pass the tests. So that's why unit testing is useful. And if we look at the V model here, we can see that this triangle here is essentially how we do test-driven development. So basically, we normally we just design first, write code, and then do testing. And for test-driven development, what we do is we write the test first, and then we do the design first, then we do the write tests, and then we do implementations to pass the test. And so we just change the order here. So this is why unit testing is important. And the key thing here is what is a unit for a program, because we need to find out the atomic unit. We need to find out the smallest module, and what is exactly the smallest module, or what is exactly a unit here. So different programs may have different definitions, but normally it is considered as a function or a method. And in object-oriented programming, you may consider a unit as a class plus all its methods. But we will cover more about how to test OOPs later. And let's do a level poll. So based on what we have just learned, so do you think unit testing is normally considered as a white box testing technique or a black box testing technique? Actually, but not everyone has done the poll, so let's wait maybe for more students to come. Okay, we got one correct answer at least. So normally unit testing is considered as white box testing because I just mentioned one advantage or one motivation of doing unit testing, learning unit testing at least, is that it is part of the testing-driven development process. So when we do development, we have the source code, right? And we can apply. When we do unit test, most of the time we assume we have the source code, and we design the test cases according to the properties of the source code. For example, we can do boundary interior testing. We can check the conditions of the loop. We know the source code, so normally it is considered as a white box testing technique. If it is considered as a black box testing technique, then it is not part of the test-driven development process, right? If a developer must have access to the source code, so that's why it is normally considered as a white box testing technique. We have one more correct answer. And let's continue. That's all about unit testing today, but that's not all about unit testing for this course, because you may have learned that there are many unit testing frameworks for different programming languages. Actually, for almost every programming language, there is a unit test framework. And this actually helps us to somehow automate this unit testing process. And we will learn that later. And we will also learn how can we generate unit test suites automatically near the end of this course. So, but this is just an introduction to unit testing in the context of different levels of testing. And now let's move one level upper and learn about integration testing. So integration testing is also known as subsystem testing. So when you encounter this term, you will know that it is actually referring to integration testing. So the rationale here is that most software works by combining multiple different individual components, and there could be bugs inside each one of the components. There could actually also be bugs when the components interact with each other. So how can we test the interaction between different components? We can't do unit test again, right? Because for unit test, we are not aware of what's happening outside the component. So how do we test the interactions of components? We have to somehow combine them together into larger components and test them together. So this is the motivation or the rationale of doing integration testing. So here the question or the key point is, how do we determine the subsystems? Because if we have a very large piece of software, we have many different smaller individual components, we can combine them or use them in multiple different ways. So how can we systematically determine the subsystems here is the key. So we have different strategies to do this kind of integration. So the first one is we can do decomposition-based integration. So for this type of integration, we have multiple different smaller integration strategies, and all of them are actually based on an important concept called functional decomposition tree. So again, this is some kind of boring concepts. So a functional decomposition tree is actually a visual tool to break down complex systems or processes or functions into smaller or more manageable parts. This method helps to understand how different components interact with each other. So as the name indicates, it is a functional decomposition tree. So it means that we are trying to decompose the software according to the functionalities. So that's why it is called functional decomposition tree. And it actually helps us to identify how different components interact with each other. And for a functional decomposition tree, there are many different important sub-modules. So the first one is we have some kind of top-level functions. Normally, this top-level function is the main function of the program. And then we have some sub-functions, like the first layer after we enter the main function. So these are the top-level functions. And of course, sometimes we could do some further decomposition to really describe more details about the design of the system. So normally we have these 3 layers. And this is the workflow of identifying a functional decomposition tree. So the first one is we need to identify the main function in the system. And that actually corresponds to how we determine the top level function. And then we divide the main functions, and we define the relationships between the different components of the divided, between the different components divided from the main function. And after that, we can represent the relationships by connecting them into a tree. And then we can, if it is needed, we can further refine the decomposition to add in more branches or leaf nodes to include more details. As you can see here, the key of functional decomposition tree is to identify how different components interact with each other. So we need to define the relationships. And sometimes, if needed, we may need to have more than one layer in the tree. So I see some of you look quite confused. So let's have a quick look at an example of what is a functional decomposition tree. And let's consider this calendar program. So here are some functional requirements for this calendar program. So the first requirement is we need to be able to get the date of the next day, and we have learned about this. We have used this next date example in many of our lectures before, and this calendar must be able to identify the leap years, and it should also be able to identify the day of the week corresponding to the date. And we also wanted to be able to identify the zodiac sign of the date, and we wanted to keep track of some memorial days, and we also wanted to report the most recent Friday the 13th. And talking about Friday the 13th, you may think about this, but we are not talking about this one here. So this is, if we try to do a functional decomposition tree, what we can get is something like this. So in the very top layer is the first component we just introduced, the main function. So basically we should have a root node for this tree. So like every tree, we should have a root node. And then we should have the first layer of all the sub-functions described in this requirement. And sometimes we may want to further decompose the functional decomposition tree to describe more details. For example, in this example here, we may further decompose the getDate function into isValidDate or getDigits from the user input. And for the next date, we may need to consider the function of converting the number of a day into an actual date. And for Friday the 13th functionality, we may need to consider having a functionality of checking whether a day is a Friday or not. And for memorial date, we may, in this example here, it actually considers whether that day is a Monday or not. And as you can see here, we can also do some further decomposition to add in more layers. But this is a rough idea of how we build functional decomposition tree. So basically, we just follow the functional requirements and try to decompose according to the requirements. And as you can see, this is actually closer to black box testing because we are not dealing with actual code. We are dealing with requirements or functionalities. And let's see what kind of decomposition or integration strategies we can build based on this functional decomposition tree. So the first one is we can do top-down integration. So actually in top-down integration, we begin with the main program or the root node in the tree. And any lower level unit called by the main function is considered as a stub. And a stub is a piece of throwaway code that emulates the called unit. So we don't really need to have the actual code of the stub. So it actually is like a dummy code or like maybe a switch, or maybe just a mapping between inputs and desired outputs. So we don't really need to implement or have the implementation of those stubs. And this is an illustration of this main function and the stubs. So in this case, we can use some dummy code to replace the stubs here. And once all the stubs of this main function has been provided, since those functions are like throwaway code, which can mimic the original behavior of the actual implementation of the sub function there. So this piece of code of the main function could be executed for testing. So we test this main function and all the stubs and all its stubs as the first integration session. So in the first session, we test the main function with all the stubs here, and we can actually hard code the correct response in the stub. It's not the actual code. And once we have and that's the first step. In the previous example of the calendar program, what we can do is, if the main function calls the zodiac checking function, what we can do is we can just generate a stub function that can return the correct answer for some particular user inputs to mimic the correct behavior or the expected behavior of the program. So this is what we can do for that example here. And for the stub, during the integration session, once we have all these things, we can apply different functional or structural testing techniques to look for faults inside this main function plus stubs. And once we are convinced that this integration of the main function and the first level of stubs is correctly implemented, we can move on to the next layer. We can try the first stub. We replace the stub with the actual code. And if this stub has some other layers under this one here, we generate stubs for this code. So we are doing it layer by layer. And do you think this is BFS or DFS here? So the way we do top-down integration. Normally we do BFS, so we try to do it layer by layer. Since we have top-down integration, we will have bottom-up integration. So for bottom-up integration, it is like a mirror image to the top-down order of doing this integration testing. So instead of stubs, this time we have drivers. So you may encounter the term driver later when you learn fuzz testing. So driver modules are actually because we are doing bottom-up, so we need to provide context for the unit we are testing. And this driver is like providing the original context in the target program for the unit we are testing bottom up. So this is an illustration of how we do bottom-up integration. So for each module here, instead of having a stub of like a dummy code replacing some of the functionalities of this piece of module, we use a driver to provide execution context for this module here. So this is called bottom-up integration. And in bottom-up integration, we start with the leaves of the integration tree. So we are doing it bottom-up, and then we test each one of the leaf with specially coded drivers, which are like providing the parameters or providing the preconditions or prerequisites for executing that module or that piece of code. And as you can imagine, we have less throwaway code in drivers than in stubs, because we are actually, because for drivers we are starting from the very top level, and we assume everything is not implemented. We have to replace them with some hard coded responses or return values for each one of the sub functions. So that's why we have a lot of dummy code or throwaway code in stubs. But for drivers, we are doing it bottom up. We are starting from an actual implementation of a particular module or a particular unit. So we have less throwaway code in this sense. And since most systems have a fairly high fan out near the leaves, which means that the bottom layers of functions, they may call a lot of other functions. So in this bottom-up integration order, we will not have the problem of having too many drivers in this sense. So all these modules here, if they are called by one function, we can use one driver to test all of them. So that's why we don't have to worry about having too many drivers here. And since we have bottom up, we have top down, we have bottom up. What we can do is we can also have sandwich integration. So for sandwich integration is like a combination of top down and bottom up. And what we do is this actually helps to save the development effort for stubs and drivers. But since we are testing a larger piece of code, we may have problems to isolate fault. So the ultimate goal of testing is actually to find out to not only to tell there is a bug in this piece of code, but also to tell where is the bug in this piece of code. And in sandwich integration, it is often hard to do this fault localization or isolation. And this is an example of a sandwich integration for this get date function here. So a sandwich integration is a full path from the node, from the root to the leaves of the functional decomposition tree. So it is more like a subtree derived from this original big tree. So this is sandwich testing. As you can see here, since we have included more components, it's harder for us to really isolate the fault once we have found one. But it is kind of easier for us to isolate the fault we have found in bottom-up and top-down integration, because once we have integrated a new stub, or once we have replaced the stub with actual code, and then if the program runs into error, we could definitely or clearly tell that the newly replaced stub, the code of the newly replaced stub is buggy. So that's why top-down and bottom-up are easier for fault isolation, but sandwich is hard for fault isolation. And one last integration strategy for this integration testing is called big bang integration testing. So big bang integration is actually where we put all the components and modules together as a single unit. So sandwich is more like a subtree of the big bang. So big bang is just test the entire functional decomposition tree. And wait, you may think that, okay, if we combine everything together, if we combine every component together and test them together, then what's the difference between the big bang testing and system testing? What's the difference between them? Actually, the difference between big bang integration and system testing is the boundary is quite blurred. For big bang integration testing, it is still considered as an integration testing, so it still focuses on testing the interactions between different individual modules. And since it is based on the functional decomposition tree, so we are still designing test cases or test strategies to test these functionalities or integrations between or interactions between different functionalities. So that's why that's the first difference. So this big bang integration testing focuses more on the interactions, while system testing tests the performance or the functionality of the entire system. So we don't care about the interactions between different modules inside the program when we do when we do system testing. That's the first difference. And the second difference is that since big bang integration is still an integration testing, so in the V model, you could see that it is actually normally performed after we have finished unit testing and before we do system testing. And that's the second difference. But that's not really a technical difference. So that's all about big bang integration testing. And here are some pros and cons of using decomposition-based integration strategies. So there are actually two advantages of using these type of integration strategies. So the first one is whenever a failure is observed, the most recently added unit is suspected. So for top-down, whenever we convert a stub into an actual code and there is a bug, and if there is a bug, then we can tell exactly that this newly introduced code is buggy. And it's the same for bottom-up. So whenever we replace the driver code with the actual implementation of that piece of code, then if the program runs into some errors, we can tell that, okay, there's a bug in that piece of code. So this is the biggest advantage of using decomposition-based integration testing. And the second one is, since we are designing the decomposition strategies according to this functional decomposition tree, so we can easily track our testing progress according to this tree. And there are some drawbacks of doing this kind of functional decomposition. So the first one is that as you could see for the calendar program example, the functional decomposition tree is actually not derived from the code, not based on the code, not based on the implementation. It's more based on the functionalities. And most of the time, requirement engineering are not, many companies, they don't do requirement engineering at all sometimes. So when they develop, especially for some internal software, they develop for other teams in the same company. They don't really do a very formal requirement engineering. They don't do this kind of functionality or specification writings. So this functional decomposition tree is somehow more like an artificial thing that is particularly useful for project management more than development. So developers normally they don't do this. So this is this may introduce some extra burdens when you do actual development. And again, for some of the decomposition strategies like the top-down or the bottom-up, we have to write stubs and drivers, and this will introduce more efforts to the developers. So this is actually another drawback. And here are some factors that could affect your choice for the decomposition strategy. So first, if there are clear requirements and design, we may consider doing some top-down approach. We can use top-down approach because we can easily write stubs if there are very clear requirements. So we can easily write some hard-coded functions if the requirements are clear. And if the requirements keeps changing, in that case, we may want to do a bottom-up approach, because if every time a requirement changes, if we do top-down, we need to redo a lot of testing. But if we do bottom-up, since we are testing from the smaller units, so if small unit gets changed, then we can only test that particular unit. So we prefer bottom-up if the requirement changes very fast. And if we are changing some architecture, or the design is relatively stable, so maybe we don't want to make big changes for our software, then we prefer sandwich. And if the changes are really limited, so we don't do very, very big changes, we can also consider big bang to test everything together. So these are some factors that may affect your choice of integration strategies using this decomposition-based integration. And let's have a 10 minutes break, and we will continue at 3:02.
Ask you after the lecture if that would be a good time, or should I?
Yeah, maybe you can ask him now. If it is interesting to others, I can also tell them.
I'm a little unsure about the equivalence classes. I don't know if it should be like split like this, or if it should be like that, and if this is a good way to go about it.
Yes, you need to consider whether it's invalid or valid.
Yeah.
So this is a good try. And what else do you want to ask?
It seems like this is a lot, so I don't know how I'm supposed to like generate passwords for every single.
Oh, you don't know how. You need to write a program to generate version for 1.2.2 if you think there are too many combinations.
Are we expected to find a lot of combinations? Because I'm not too sure if this is going about the right way.
You can actually convert it into some if-else conditions, right? And you can use those conditions to write a program to generate test cases. So the lecture is more about learning how things work, and the assignment is to practice how to use programs to automate this process.
Okay.
So yeah, I think this looks okay, but I can't tell you whether it's good or not but looks okay.
Does this include this? Is this like, should it be split like that? All the valid test cases? Or like that? Or should I just have like, I'm not,
This looks acceptable for this question.
okay.
But if you want to use it for generating test cases, oh, you have done that, right?
This wasn't like generated. I was like, this is
not
too
exhaustive.
much.
Yeah,
Yeah.
not exhaustive.
So,
If you want to generate a comprehensive test suite, you have to write a program.
okay.
Yeah.
What about for the decision table? Because isn't that going to be quite a big table as well?
It's a big table. You can use Markdown to draw that table. It's not very big.
Not
very.
because I'm not too sure. Hang on. Just because we were supposed to do an extended entry decision table, but this is the only thing that I could think of for that would
Yeah,
help.
yeah. This is
Should
kind
I?
of correct.
Are there more? Where there's
I can't tell you because I'm giving you the answers if I was telling you everything. But you can trust yourself and don't overthink.
okay.
Yeah.
So would it be fine to just do it like this?
Okay, it's acceptable. But you have to convert it into a Markdown table.
Okay.
Yeah.
And you reckon if I did it like this, the table wouldn't be like too big?
Wouldn't be too big because the size of the table is determined by the number of rows, so you won't have too many.
I'm not too sure. It seems like
Yeah, this is not very big.
okay. These two, you wouldn't be able to merge them, would you?
I'm not telling you the answers.
So
this
where
has
can I
not-
go to for help then? Because
you have to reason. You don't just go for help. You have to reason about whether it makes sense or not. Maybe I can give you an example here. So let's say, for example, this one here. This doesn't seem to be impossible in this case.
why not?
Because impossible means they are conflicting.
Yeah. So if doesn't this conflict if it doesn't contain this? How can it? Oh, sorry. No, that should be. Yeah, this should be. So this would be conflicting.
Yes.
Yeah. Okay. So, sorry, I messed up the conditions, but
Yeah, but you have to reason. You just do this kind of reasoning too.
what do you mean?
Because for impossible ones, right, you just try to find conflicting.
Yeah, but
conditions.
so these would both be impossible, right? But
Yeah.
could I merge them? Would it make sense to merge them? Or no?
No.
No?
No, it doesn't make sense to merge them.
Could you explain why? Just because I want to understand.
Because in the example in the lecture slides we merge the dates, right? So this one here is it's actually because we can't merge them because we assume the whole password is like that. That
Yep. So if it's the same here,
yeah. So we can't just merge them because they are the same here. How would you deal with these two cells? You can try to merge these two rows.
okay.
Problem.
So it's not because like
Yeah.
the height.
Yeah. And also because we assume the whole password looks like that. What about digits? What about special characters? We can't assume that. So it's better not to merge because the whole password comes from here.
Okay. All right. I guess I'll keep working at it. But so for this one, just write a program that.
Yes.
Okay.
Try to somehow convert your rules into
was for the poll. You said the unit box text for the unit tests white box testing.
Normally it's considered as white box testing.
Because you mentioned test-driven development, right?
Yes.
And that's written before the implementation. So if you've written the test before the implementation, how can it be?
Sorry, that's not a good example here. So normally normally unit testing are written by the developers, not by the external testing team. Yeah. And the developers normally have the source code of the program, of the tested target. And another reason here is even for test-driven development, when you have implemented the code, you may want to enhance your tests. And when you enhance your tests, you may try to consider your actual implementation. So that's why we consider, because the main reason is because it's done by the developer.
But isn't that only true if the developer does that after he's written the implementation? Because if you write a
yes. That's a good point. Yeah. That's actually a good point. Okay.
Yeah. And another question.
I will explain it in the second half. Yeah.
And for the assignment, I was just looking at it. But for the boundary value testing, should you convert some of the specifications to fit boundary value testing, or should you just use it as is? Because
you should just use it.
Okay, so you shouldn't try to convert it.
Yeah, don't try to change that.
That's it. Thanks.
Okay, let's start our second half. But before we start to look into more integration strategies, one of you just made a good point about the live poll question here. So do you consider unit testing as white box or black box? So because I just used the example of test-driven development, and for test-driven development, test cases are written before you write the test code, the source code. So how can it be white box, right? So actually, this unit testing is considered as white box normally because it is normally written by the developers, not by the testers. And developers do have access to the source code they have written. And even for test-driven development, you may not normally you don't have just one version of tests. You may want to upgrade your test cases once you have done the implementation. So that's why unit testing is considered as white box. It's mainly because it's done by the developers. So that's why. And you look even more confused. So do you have any questions? Or no? White box. White box. Yeah. And white. I said white. Yes, white. Oh, that's why you look confused. Okay. Yeah, it's considered white box because it's normally considered done by the developers, and we assume that the developers have access to the source code, so that's why. And let's continue. So integration testing is all about different integration strategies, and we have just learned one integration strategy according to functionalities of the program. So that is about the requirement. So can we develop integration strategies according to the implementation of the code? And the answer is yes. So the first type of integration strategy based on the implementation is called call graph based integration. So the rationale is like this. So one of the drawbacks of decomposition based integration is that it is based on the functional decomposition tree. And the functional decomposition tree is developed based on the requirements and or specifications of the program. So it is actually not related to the actual implementation of the code. So what we want is we want to consider how the code is actually implemented when we do this kind of integration of different components of the program. So this is why we come up with the call graph based integration. And you may wonder, okay, what is a call graph? Then a call graph is actually a particular type of control flow graph that represents the calling relationships between different subroutines in a computer system. So the terms used here are actually quite accurate. So they don't use the calling relationships between different functions or methods. They use the name subroutine. It is because in some special cases, like in C, we have the go-to statement. We can go to a label. So in that case, the labeled code or the labeled routine could be considered as a called target. So but this is this is just some corner case. So each node in the call graph actually represents a procedure, and each edge indicates that this is it is a directed graph. So each edge from one node to another means there's a call from one node to the other. So this is the definition of call graph, and this is an example call graph based on the calendar program we just used. So you can see that the main function is calling some other functions, and different functions could have different callers and callees. So this is a call graph, and we can use this call graph to do integration, to integrate individual components. So the first one is we can do pairwise integration. So the rationale here is that we want to eliminate the stub or driver development effort. So remember, stubs are like the callees, and drivers are like the callers of the program of a particular unit. So instead of developing the stubs and drivers, so why don't we just use the actual code at the start, right? So in order to identify these stubs and drivers, we have to find them from the call graph. So that's why we need the call graph. And because we are also interested in testing the interactions, so we have to test multiple components together at one time, and multiple related components together, actually. So in this case, we restrict the integration session to only a pair of units in the call graph. And this is an example of pairwise integration. You can see that we can pair the nodes up to see to check whether they are there are some interaction errors between these pairs. So the main advantage of pairwise integration is that it has a high degree of fault isolation. So if a test fails, the error must be in one of the two units, right? At least one of the two units, or their interactions. And the biggest drawback is that it actually involves several pairs. It is sometimes, because the unit is too small, it's only a pair of functions normally. So sometimes an error could involve multiple different pairs. And if that happens, it's actually hard for us to really fix this kind of errors. So this is this is the biggest drawback of pairwise integration. And actually in this graph here, these two pairwise integration are not considered so valid, because these two pairs they don't have an edge connecting them. So in this example here, these two are not considered as valid pairwise integration. What we want is because we are trying to test the interactions between different nodes, so there must be an edge. We are interested in testing the edges of call graphs. So what we want is to cover all the edges of a call graph. So that's why these two, this is actually a screenshot from the textbook, and these two actually are not valid pairwise integrations. So let's do a second lab poll today. So based on what we have just learned, so how many test sessions do you think we need to do a comprehensive pairwise testing, pairwise integration? So remember, the aim is to have one integration test session for each edge in the call graph. This is actually very straightforward. Actually, the correct answer is 19. So you just need to count the number of edges here. So maybe you have counted wrongly, but yeah, but like I just mentioned, we try to, maybe I'll highlight it here in this slide. So we try to have one integration test session for every edge in the call graph. So the number of integration sessions or test sessions we need is purely depending on the number of edges. So you just need to count the number of edges in this call graph, and the correct answer is 19. And I won't count it here. You can count it later, maybe. So let's continue. So, hey. Uh-huh. Yes.
In this integration test, if we're only using one test for each time the function is called, isn't there more inputs, more ways we can test how the function is being called?
Oh, a test session doesn't mean one test case. It means a target we choose to test. So for different levels of testing, we are not dealing with how we generate test cases, but we are dealing with which target we are testing with. For example, for unit testing, the target we are testing are each functions in the software. For integration testing, we are testing smaller components of the software made up of some functions, so made up of some basic units. So for each test session here, for each target here, we can generate multiple different tests. So that's the idea here. So so let's continue. So apart from pairwise integration, you may think that, okay, it may give us too many targets to test because we are testing them pair by pair. So what else can we have is that we can test a neighborhood of units altogether. So normally, if we don't specify anything, a neighborhood of a node is considered as the set of nodes that are one edge away from the target node we are trying to test. So in a direct graph, because COP graph is a directed graph, so it actually includes all the immediate predecessors and all the immediate successors of a node. For example, for this node 16 here, node 1 is the immediate predecessor, and node 9, 10, and 12 are the immediate successors. So we are trying to include all of them as the target we are testing here. So this is how we do neighborhood integration. And this, by default, we assume that the neighborhood are within one edge from the target. Actually, this is technically, this is called a neighborhood of radius 1. And this neighborhood of radius 1 is normally enough for most of the systems. But in some larger systems, in some larger software, we may consider to increase the neighborhood radius to include more nodes into a particular neighborhood. And neighborhood integration actually helps us to reduce of integration sessions. So it actually helps us to reduce the number of targets we are trying. And you can see that. This is also similar to the idea of writing drivers and stubs, which are providing because we are trying to, for node 16 here, for example, node 1 is actually could be considered as the driver for this node 16. And the nodes 9, 10, and 12 could be considered as the stubs here. So it actually also it also echoes the concepts of stubs and drivers here. But since we are using the actual implementation based on the COP graph, we are actually avoiding the development of stubs and drivers. So this is the advantage, and the end result here is a neighborhood, and this neighborhood is actually it actually looks like a sandwich of this COP graph. From this COP graph, it actually echoes the concept of sandwiches. So, but remember, for these sandwiches and stubs or bottom-up, top-down decomposition methods, they are not related to the actual code implementation. They are more related to the functional requirements. But here we are dealing with actual code. So this time we don't do a live poll. Let's save some time. So based on what we have learned just now, how many test sessions do you think do we need for this calendar example here? So how many testing targets can we derive for this example to do neighborhood integration? Do you have an answer now? 15? Yes, that's correct. So we need 15 neighborhoods or 15 targets to test. And the reason is that we can't get one neighborhood for every node here. So instead of counting the number of edges, this time we count the number of nodes or the number of functions in this COP graph. So that's why we need 15 targets or 15 test sessions for this neighborhood integration. And here are the advantages and disadvantages of using call graph-based integration. So the call graph-based integration is actually more towards structural testing, because call graphs are derived from the source code of the target. And these call graph-based integration strategies also helps us to eliminate the effort for developing stubs and drivers. The reason is that it's quite obvious, because we are dealing with actual code. And these techniques actually also matches well with the development characterized by builds, which means that we are because we are actually developing the actual code, we are saving the effort of developing the stubs and drivers. So once we release the build of the software, we can quickly test that software using these technologies. So that's why this techniques matches this kind of development style. And however, there are some drawbacks of this type of call graph-based integration. So the biggest drawback is still the fault isolation problem. So especially for neighborhood call graph testing, if we do pairwise, of course, we can easily isolate the fault, but we will face the problem of having too many pairs. But if we use neighborhood testing, and if we set the radius of the neighborhood to a larger number, then we may face a problem of the localizing or locationing the bug we have found. And another problem is with this kind of call graph-based integration strategy is that sometimes a node or a unit could appear in several different neighborhoods if we do neighborhood testing, or even if we do pairwise testing, a node could appear in many different pairs. And if we imagine we found a bug with such a node, and we fixed that bug, and we need to replan our test. We need to redesign our test to test out whether we have patched, whether we have fixed the program or not. And then we need to test all the related neighborhoods, all the related pairs again. So this will require a lot of retesting efforts if we found faults in those kind of nodes. So this is another drawback. And now let's come to the last integration strategy. So for decomposition, we have top-down, we have bottom-up, and in between top-down and bottom-up, we have sandwich. And similarly, for decomposition-based integration, it is somehow more towards functional testing. And for call graph-based integration, is more towards structural testing. So do we have something in between, like the functional testing and structural testing? So we do have that, and that is called path-based integration. And for path-based integration, we need to introduce more terminologies here. So this is an example, a very simple control flow graph we have used before. And in this control flow graph, it is actually not very accurate. Why? Because in this basic block here, the program calls the function add. In the block 2 here, it actually calls the function add. And once the program calls a function, it actually gives the control away to that function, right? So we should actually have a branch pointing to the function of the add here from this control flow graph, but we don't. But in our previous control flow graph generation, we don't consider this, and this is actually a corner case for control flow graph generation in many different cases. But the most accurate way of controlling of generating this control flow graph is to have a separate branch for each function call. So remember, this is not the most accurate control flow graph we could have. So let's introduce more terminologies here. So the first one is called statement fragment. So statement fragment could be considered as a basic unit of the program. For example, we could consider a basic block in the control flow graph as a statement fragment, or we could consider, so it's basically multiple statements executing in one sequence. And we could also consider maybe a larger scope, more related to those functional designs, as a statement fragment. And the second one is called a source node. A source node, since we are dealing with graphs here, so we are dealing with nodes on the graph. And for nodes on the graph, one type of node is called a source node. And the source node is actually the nodes where the statement fragment, where the program begins and resumes the execution. So different from what we learned before, because we are not branching, we don't have branches for function calls. So normally one program will only have one starting node, but for source node, we could have multiple source nodes, because we may return back from the program and execute again. So for block 2 here, so for this very simple program, for this very simple call graph, once we have returned from this add function here, actually we can think that this program continues or resumes its execution here. So this resume point is, or this resume node is also considered as a source node here. So basic block 2 is a source node. And of course, basic block 1, which is the starting point of this control flow graph, it is also considered as a source node. And we have starting points. It's normal to come up with end points or exit points. So instead of calling them end or exit, we call them sinks. So this is somehow similar to the terms used for data flow analysis. So we have sources and we have sinks. And for a sink node, we consider it as where the program terminates or the program transfers control to other units. So for example, here in block 2, we are transferring control to add here. So before when we execute this statement, so block 2 is also considered as a sink. So this block 2 is actually both a source and a sink. And of course, the exit node is a sink. Since we have source, we have sink, we could have module execution path. So module execution path is a sequence of nodes flowing from source to sink. And there shouldn't be any intervening sink nodes in between. So one MEP or one module execution path should only have one sink node. So this is one source and one sink. So this is called a module execution path, and it is called module execution path. So it means that we are still dealing with one module here. And in order to interact between modules, we define a new term here, which is called message. A message is a programming language mechanism where one unit transfers control to another unit. So there could be different implementations depending on the programming language. For example, we could have function calls. Of course, we could have some subroutine invocation methodologies, like using some message queues in some programming frameworks like Android. You may send out some intent to transfer the control from one activity to another, like in some more complex systems, you could use message queues. And of course, the most basic ones are the procedural calls, the function calls, or the gotos in C. So we could have different methodologies to transfer control from one unit to another, and all of them are called message here. So we don't want to deal with a particular implementation. We don't want to deal with a particular programming language. We are learning some kind of a very general methodology here. So this is called, so the way of transferring control in between modules is called message. So you just need to know that. And we need to learn more. And the other terminology to learn here is called module to module path, or MM path. So an MM path is an interleaved sequence of module execution path and messages. So in this one here, this is an example. We have 3 different modules, A, B, and C. So each one of them, you could consider each individual one of them as an individual control flow graph. And of course, this MM path, since it's a path, it should be directed here. This example is not very accurate. And with this MM path, we can build an MM path graph. So the definition of this MM path graph is that given a set of units, the MM path graph is a directed graph where the nodes and execution path and edges, where the nodes are the module execution paths and edges are corresponding to messages and returns from one unit to another. So the effect of this definition is that the program graphs now could have multiple sources and sink nodes. So this is how we define this MM path graph. And let's have a look at an example of one single MM path. So this is more accurate representation of this MM path here. So we have 3 modules. The first one is module A, where all the nodes are denoted as A1 or A2, A3 or A something here. And we have a module B, where all the nodes are denoted as B1, B2, B3, B4, and B5. And we have another module C here, known as C1, C2, and so on. So let's try to practice with the following questions here. So what do you think are the source nodes of A according to the definition we have learned? The source nodes. So the source nodes are defined as where the execution of a unit or a module starts or resumes. So what are the source nodes for A here, for module A here? Where the execution starts or resumes. So start means quite obvious, A1 is the start. And resume means the control is transferred back to this module. So is there any node where the control is transferred back? Sorry, I somehow leaked the answer here. So yeah, the A1 is included because it's a start, and A6 is included because it is the point where this program resumes execution, because the control is flowing back from module B to module A through this message 1 return here. So this is why A6 is a source node. And similarly, what are the source nodes for B? And this should be quite straightforward, right? So I think some of you may have already got the answers. So the first one is B1, because B1 is the start of this unit or this module. And the second one is B2, because B2 is where the program, the execution of module B resumes. So B1 and B2. So, and what are the sync nodes for module A? What are the syncs for module A? So syncs are where the module terminates or it transfers control to other modules. So it's actually a mirror of source. So syncs are like mirrors of source. So it's where the program terminates or transfers control to others. So what are the nodes for A? Sync nodes for A? I think you have got the answer right. So A8 is obviously a sync because it's where the program terminates. And we need to look for where A transfers control to other modules. And because modules, according to the definition, modules transfer controls using messages. So they should be A4. So A4 is transferring the control from A to B using message 1. So A4 is another sync. A4 is another sync. And instead of asking you what are the things for B, it's quite straightforward. Let's try another question here. So what are the module execution paths for A? Module execution paths are considered as the path from the sinks, from the source to the sinks. So what are the MEPs for A? We have sources, we have sinks. Sorry, I made a typo here. This should be A4 and A8. A4 and A8. I will correct it later, but I won't do it now because I will leak the answers. So what are the module execution paths for A? So it is defined as the path connecting sources and sinks. So let's do it. Let's try to find out what are the MEPs according to the definition here. So A1, of course, is a start of a path, right? So we just traverse through this graph and we could reach A4. And we have to stop here because each MEP should have only one source and one sink. It doesn't allow intervening sinks. So if we don't stop here, and if we try to build a path from A1, A2, A3, and A4, and A6, A4 actually becomes an intervening sink. So it actually conflicts the definition. So that's why we should stop here and use A1, A2, A3, A4 as the first MEP. And let's try to find out other MEPs So we could have, because A1 and A6 are all the starting points, right? So what we can have is, we can have A6 as the starting point, A6, A7, and A8. And of course, and actually that's all. I think there's a typo here in this page. So that's how the module, level execution path for A. And why this is helpful for testing, for integration test, I will correct this page after I presented this one. So the module execution, we can, this actually provides another way of doing integration, because we can actually carve integration of components based on the path here. So it is like how we do path-driven or path coverage guided structural testing. So we can use each one of the paths here to build integrations. So that's why this makes sense. And there are some errors here. So the sinks should be A4 and A8, because A8 is a terminating point. And since A4 is not an end, we shouldn't start from A4, and we should only start from A1 and A6. So these are the two module execution paths according to the definition. And let's come to the pros and cons for this type of path-based integration. So like we just introduced during the start, so we have function level, we have some integration strategies that are towards functional testing. We have some integration strategies that are towards structural testing, and we do have something in between. And path is actually that thing or that strategy in between. It is because it is considered as functional, because we are representing the actions with inputs and outputs. So we are actually trying to generate this causes and effects of the of each one of the paths here. And the structural side, the structural aspect actually comes from how this path graph are identified. We can build them on top of control flow graphs. So this is why it is considered a hybrid of functional and structural testing. And another advantage is that the test cases or the testing targets we have designed based on this path testing actually is closely coupled with the actual system behavior, because we are not purely deriving the path from the functional. We are actually considering the actual implementations, and since it involves multiple, it uses messages to glue these components up. It actually somehow reflects how the developers try to design the software to reflect the requirements. So that's why it is closely coupled with how this system will actually behave. So this is why these are the advantages. And the disadvantage of this technique is that, as you could see, path is the graph of path is very tedious, and it often requires a lot of effort to develop that graph and path. And since it is a path-based development, we may face the problem of path explosion, just like what we have seen before with structural testing. And however, this is not all. It's not all about bad things. The good thing is that it can still somehow help us to eliminate the development of stubs and drivers, because we are dealing with actual code using this path graph. So these are the advantages and disadvantages of integration testing. And before we end the class today, let's have a quick review of what we have learned today. So we have learned different levels of testing. So what we have previously learned are functional testing and structural testing, and those testing techniques helps us to solve the problem of how do we design test cases. And today we learn different levels of testing. This actually helps us to determine the problem of which target should we test. So given a very big piece of software, should we test it as a whole? Should we test it as smaller units, right? So actually different levels of testing helps us to solve the problem of which targets do we want to test. And the design of different levels is closely related to the software development life cycle. So remember the V model. For each stage of the software development life cycle, we have a corresponding testing plan. So for requirement, we have system testing. For architecture, we have integration testing. For design details, we have unit testing. And today we learned from the bottom up of the V model. We learned unit test first, which is the most straightforward one. We try to identify the most basic units of a software, of a program, and test it. And the definition of unit is important here, right? So normally a unit is considered as a particular function. And of course, for object-oriented programming, we may have some small variants. And for integration testing, it is all about how do we build up this integration. And we have learned three different major strategies to make integrations of different smaller units. So the first one is decomposition-based integration. So decomposition-based integration is based on the functional decomposition tree. And this functional decomposition tree, as indicated by its name, is derived from the functional requirements of the program. So it is more towards functional testing. And the second major strategy we learned today is called call graph-based integration strategy. And call graph-based integration is based on the call graph of the program. And the call graph is a particular or specific type of control flow graph. It mainly deals with function calls. And this compared with decomposition-based integration, it is more towards structural testing, because we are actually dealing with source code. And of course, there are two important concepts here: stubs and drivers. And all the designs of this call graph-based, even though they don't directly use stubs or drivers in call graph-based decomposition integration, their design could echo the concept of stubs and drivers, right? They are saving the efforts for doing that. And of course, we have something in between functional and structural testing, and that is called path-based integration. So where we try to connect different modules with messages, and we try to deal with the control flow across different modules. So this is this is somehow like in between functional and non-functional or structural testing. So that's all about what we learned today. And in our next lecture, we will learn about system testing and how can we somehow automate the construction of test cases. So that's all about the lecture today. And thank you.
CFG, when you want us to write the subpaths, you want it like, is it fine to just write it like this, for example? Like this is following how it basically was in the lectures, or did you want it like, is it supposed to go and then
Because
that.
we will,
Because
our
like,
custom means we manually review your answers. So it's better to make it easier for them to read. For example, you can use BB instead of just, this is a line number, right?
oh no, this is the
Oh, BB.
I'll put BB in front of it.
Oh,
But
I see.
I was asking like,
Yeah, you can do this. You can do this.
yeah, so as in like each subpath just started from like that and then back to that. Is that fine, or do you want it? Is that how you want it written out? Or?
This is fine. As
Yeah?
far as, yeah, this is fine.
Okay. I had another question. Is there a reason it's limited to 3 or
Because
for
I
this
don't have,
case?
you can limit it to any
Okay.
range or use any number as a limit here.
Mhm.
It's just because I don't have enough space to put it here.
And just
But it's also partially because when we do testing, we mainly consider 0, 1, and 2,
Mhm.
2 or more, right? So
Yeah.
limiting to 3 is safe enough.
Okay.
to
And
use most
another
cases.
thing with this, do we just assume that this is always like the previous?
This
'Cause-
is just an assumption. You can.
So does that mean that if we wanted to write like a test case that didn't fit that, then we'd just assume that that was the previous?
Yes.
Okay.
When you write a test case, you should assume this.
Does that also hold true for like this? As in like we should assume that that is the previous password if we wanted to do something like, let's say, do we assume here that, sorry,
Actually,
do we assume, for example, that it's like,
yes. If you put it here like this, you can make this assumption here. But if you
okay, so you can make the assumption for the,
if you put it explicitly like this, you can make the assumption. But if you don't put it here, you just wrong.
okay, so we can't use this assumption for that, even though it's still the previous. So, because I don't quite understand what it's saying for the assumption, because it says assume that that's the username and that's the password. So, are we not allowed to assume that for?
You are allowed to put it here in the condition here.
Wait, so
You can allow.
so you're saying that we would also have to account for the case where that isn't the old password? So we'd have to assume that there are others? So we can't
It's actually,
assume that.
don't try to overthink here. It's actually you can just assume it's a true and false. So whether it contains old password or not.
But if I
it's just true or false.
But if I don't put this, then I can't assume that this assumption of the whole old password is true.
Yes. And
So does that mean I need to put a different one, or?
You don't put a different one. And if you don't make this assumption, it won't affect how you